So thanks so much for coming. Presenting today is Claude, so I'm really pleased to have you, Claude, doing some really interesting stuff, really practical stuff too. So it's really cool. And yeah, he has got some funding from NBIE, so it looks like a really good project. So yeah, thanks very much, Claude.
Hello everyone, I'm pretty sure everyone knows me, but just in case, my name's Claude. I've been here as a PhD student for 3 years, and before that I was here in undergrad. So today I'm going to be talking about a versatile thermal measurement system which is used for small and challenging samples. So today I'm going to be talking about two different systems or two different materials which I've measured over my time here, and then at the end of it I'm going to talk a little bit more about some future applications for the measurement system that other people in literature and also we're looking at as well. I'm also going to go quite a bit into sort of the instrumentation and how the entire system sort of blocks together and how we sort of fabricate everything. And then lastly, I'm going to be talking about a flow sensor, which is sort of the future application side of what I'm doing. So my whole PhD really started with a structure here. So this is what's called a superlattice. So it's a periodic stacking of two different materials. In these two SEM images, you're going to have to excuse the lack of scale bars. I know Block have probably already noticed that. But there are two different materials in this. The lumpy one is silicon nanoparticles, and the dark material is PMMA, which I think is commonly known as Perspex. So this is 50 nanometer layers of it stacked over 20 times in a row. So this was originally proposed in literature as something called a phosonic crystal. So this is a combination of a photonic and phononic crystal. So a photonic crystal is where you modulate the refractive indices of alternating layers to create a light bandgap, an optical bandgap. Phononic, on the other hand, phonon is a word that often people haven't heard of, but it's sort of a quasi-particle which represents the quantum of vibration energy or thermal energy. We'll breeze over most of that stuff for the moment. But in this case, we're modulating the mechanical properties of the layers, and in this way we get a vibrational bandgap in the thermal area, hopefully, as well as a photonic bandgap. So in the past, what literature has been doing with these structures, and they have been measured to have quite a substantial phononic bandgap. And we wanted to measure and see if there was a corresponding decrease in the thermal conductivity at room temperature of the structure. So we used the technique that I'm going to be talking about in a second to measure this, and we found that it actually had a pretty low, in the scale of things, thermal conductivity. It's just slightly above that of still dry air at room temperature, which is considered to be a pretty good standard for thermal conductivity. And this is pretty much equivalent with what aerogel-based materials, silica aerogel-based materials are like. And honestly, that was kind of surprising to me, at least, mostly because the whole premise of this was that we were going to get multiple coherent thermal waves crossing over boundaries and reflecting off these surfaces and sort of acting like a thermal mirror. That was the theory, at least. But the mean-free path of phonons in PMMA and silica, amorphous silica, at room temperature is on the order of like half a nanometer. So the idea that we would have thermal waves crossing all of these boundaries and reflecting seems far-fetched, to say the least. So moving on from this, we were developing theories as to why this had as low a thermal conductivity as it did. And we started thinking about pressed nanoparticle materials. So pressed nanoparticle materials are the basis for silica aerogels and the like, except instead of them being expanded into a gel. Do people know what aerogel is when I'm talking about that? No? Okay, well, maybe I'll explain that after this. So the whole premise of a packed nanoparticle bed or a pressed nanoparticle bed is that you have a ideal packing of spheres in 3 dimensions, and you have a radius of constriction at the interface between two nanoparticles. And so you have phonons which have a certain wavelength between the radius of the nanoparticle down to about the constriction, And when they are travelling through this constriction, they are sort of filtered proportional to the area of the constriction relative to the radius of the nanoparticle. So in theory, this can reduce the thermal conductivity of this material down to extremely low levels, below what's known as the Einstein or amorphous limit, which is supposedly the lower limit of what the thermal conductivity of a material can reach at a given temperature. The idea is that in the amorphous limit of the material, things are being scattered as much as they possibly could. They are as randomly scattered as they possibly could be, so it's sort of at like the limit of thermal resistivity, almost. But there are various materials which exceed this limit or go beneath this limit by imposing more order on the structure, and these pressed nanoparticle beds are one of those structures. So the idea is if it wasn't multiple coherent phonons in this structure, if it wasn't phonons traversing entire layers, perhaps an explanation for why the thermal conductivity was as low as it was due to just singly the nanoparticle layers. Perhaps this value that we measured here was just a sort of average or distance average of the silica material and the relatively known thermal conductivity of PMMA. So looking further into that, we were thinking about, given that people have measured a lot of these nanoparticle beds, what ways could we improve their performance? And we were starting to think about something called the acoustic mismatch model. So in the same way that when we were looking at the thermal conductivity of the superlattice structure, what if instead of having a homogeneous nanoparticle blend, we started to blend multiple different nanoparticles together into a composite material? So in addition to the radius of constriction reducing the thermal conductivity, we could supplement that effect by also having mismatched mechanical properties between the nanoparticles and possibly increasing the amount of thermal energy that is reflected off these constrictions. So there was actually a precedent for this in literature, and we were sort of following along with a lot of what they had studied. So the idea was that we had silica, alumina, and also carbon black. So the idea is those are three different materials which have really strongly mismatched mechanical properties, and we could start to get, well, hopefully, an increase in thermal insulating performance.
But for the specular reflection, though, you must have quite a long wavelength in the phonons compared to the size of that structure.
Compared to the size of this?
Well, the other slide you had there, with all those nanoparticles.
Yeah.
The wavelength of the phonons must be a lot bigger than the size of those nanoparticles.
The wavelengths of phonons in these materials are supposedly well represented by the bulk wavelength sort of dispersion of phonons. So they are. So I guess what you're saying is that the phonons comfortably fit inside the radius of the nanoparticles, right? Or that the nanoparticles are much smaller than the wavelength of the phonon.
Yeah, much smaller than the wavelength. Otherwise, you wouldn't get specular type effect.
They're supposedly not. The nanoparticles are much larger than the phonon wavelengths. Phonon wavelengths are tiny, like the mean free path of a lot of them are 0.9 nanometers, and these nanoparticles are on the order of 20, 30 nanometers.
Oh, that's later.
Yeah. So the whole idea is what we're going to do is get three different types of nanoparticles, mix them homogeneously together, and then press them into a disk that we could then measure using a few different methods. The first one of which was called a guarded heat calorimeter, and that's sort of the way that you probably measured thermal conductivity for those who were here in undergrad in Phys 101, where you essentially have a fixed temperature on either side and then a heat flow calorimeter, or a heat flow sensor, heat flux sensor in there as well, and then you can measure just sort of Ohm's law type stuff, temperature, current in the middle, and then you can get a thermal conductivity out of that. That's why we made this big like aluminium press, which was CNC machined in the nano lab. And so we would load a whole bunch of materials and then squeeze it to some incredibly large pressure in the megapascal kind of range, and then we would get out a structure which sort of looks like this. The cracking was sort of included there intentionally in the photo at least, because the pucks that we got out of it were actually incredibly brittle and incredibly hard to deal with. What we ended up doing, or what I ended up doing, is slicing them into smaller chunks which we could then affix to something and make them a little bit more mechanically stable. Yeah, so these were the materials that I ended up with, and I had 3 different types of compositions. They were a 1 part silica to 1 part alumina to 4 part carbon by weight, and then same order 1, 2, 3, and then a 1, 0, 1 type composition. And these were 3 compositions which had a precedent in the literature, and according to literature at least, they had a thermal conductivity of 6 milliwatts per Kelvin. So 1/4 that of the superlattice that I originally measured. So it seemed like a promising direction to go in, and that's what we went with. Right, so now that I've established that those are the structures that we're interested in, I was going to talk a bit about the thermal conductivity measurement system that I made. So this one is called the 3 omega method, and it's named this because it's a harmonic measurement system where you have an electrical signal going in at some frequency omega and the temperature of some gold thermometer that you've fabricated on the surface, which you can see here. I actually have 2 samples here if people want to pass them around and have a look. Sometimes I find people can get an idea of what I'm talking about if they actually see it. Yeah, can you see this? That's alright. Those ones are relatively unprecious. They're just soda lime glass. So the whole idea is that you can pass an electrical current through the centre portion of this line, and then you can monitor the voltage across these 2 top points in a 4-point probe configuration. And the third harmonic of your electrical driving frequency is linearly related to the temperature of the line. So why this is advantageous is in the calorimeter you have this large heating plate which so you're sort of measuring the temperatures through a derived mean, and then you have a heat flux sensor separated by some distance, and then everything's sort of separated and spread out and not necessarily inexact, but just sort of displaced from each other physically. With the 3 omega method, what you can do is you can fabricate this gold resistance thermometer directly and intimately in contact with the surface of your sample, and then pass an electrical current through it, which provides the heating, so the input into the system, and you can simultaneously measure what the output of the system is in terms of the temperature. So this has been used for a whole bunch of things over time. So originally it was proposed for exactly what I'm talking about, thermal conductivity, and this is, I'll go into some of the data processing later. But then there have also been some other variants which have come up, which all are based around having some sort of controlled experiment. And so anything basically where there's a linkage between heat and some property you want to measure, and you have a decently designed control experiment, you can end up getting some really interesting results out of it. So in the thermal conductivity experiment, what you do is you provide a sinusoidal current through it with some large or some ballast resistance, which is more than 100 times of what your actual thermometer resistance is. And then you monitor the third harmonic, which is linearly dependent on the temperature of the line. And what you find is that as you increase your electrical driving frequency, you get a decrease in the temperature response of the system. So essentially what you're measuring here is a transfer function where your input is heat energy into the system and your output is temperature. And the thermal penetration depth of some AC temperature wave or heat wave penetrating into the material is inversely proportional to the frequency with which you're driving at. The units of thermal conductivity, or power rather, are joules per second. So there's the second relationship. So if you're driving it faster, you're going to get less of a temperature response out of the system. So you can sort of see how if you start increasing the frequency, you're going to be measuring less of a depth into the material. And so your in-phase response has this sort of curve down as you're penetrating less deep into the material. And you can relate the slope of this in-phase temperature response directly to the thermal conductivity, which is the basis of this whole experiment. So like I was saying before, as long as there is some control and some linkage between heat and the thing you're trying to measure, there's actually just a really large array of things that you can do with this experiment. So just find a small sample of what I was able to find is people have been using it to measure tiny sub-millimeter biological tissue for, I think it was for biopsy applications. They needed to know it for freezing purposes. Someone has also plonked a single cell on top of one of these thermometers to measure cell viability of one single blood cell on top of the line. People have also used it to sense cell concentration and dispersion, as well as cell viability and cell health as time goes on. People have used it to sense droplets in microfluidic systems. And one thing that I'm quite excited about, I don't fully understand it, so please don't ask me questions, but people have been using it recently to sense the magnetic states of Hall crosses. So, as I understand it from the one review I've read, at least, is people are thinking of using the waste heat from microelectronic circuits to power a spintronics type circuit and use thermal energy as the readout system. So the jargon phrase is spin calatronics, which, yeah, I don't know, but I think it's cool regardless. So here are just a few pictures from literature of exactly this kind of thing going on. So this image over here is the single cell application. So they have a 3 Omega thermometer in the middle, and then they have a PDMS cell well over top, and then they've sort of just smeared a whole bunch of cells on top, and it ended up with one cell sitting over top of it. The center image is the Hall cross 3 Omega readout. So they experimented with two different ways, one where they pass electrical current directly through the Hall cross and then measured the voltage across it, Hall voltage across it, and another one where they pass current through sort of this little U-bend. Another one where they passed it through this U-bend and used non-local heating to affect the magnetic state of the Hall cross. And lastly, this is just a biological cell. I think it's some muscle tissue that they froze and then allowed it to thaw. Voltage with time instead of versus with frequency. So one of the large problems that I ran into when I was making the thermometers on top of my samples is not one of my samples is compatible with photolithography, which is the process which we make most microelectronic circuits. If you put any of my samples into acetone or even in the ultrasonic machine, anything, they just turn into a paste rather than holding their form. So I had to pursue other methods of patterning the thermometer on the surface. And with that in mind, we started using the mini mill in the lab, which is a sort of rapid prototyping and microfluidic mold milling thing. I brought sort of a microfluidic mold, which you can have a look at if they like. So this is a 3-axis milling machine that we have with an included tool probe for automatic zeroing. We have a large range of tools. The smallest one we have, although I haven't dared to use it, is 10 micrometers diameter at the tip and 30 micrometers deep. And then we have tools all the way up to 6 millimeters for large, working with aluminium and making that large mold that I showed you earlier. I've mainly been using it for shadow masking. So I mill hopefully this video's play. So I have a 50 micrometer tool on the end here, and it's going through and milling the shape that I want, and it goes straight through the material, at which point it can be removed. I really like this technique. I've used it for a lot of things, probably some things I shouldn't do, and CNC milling is a lot of fun. I just love it because it does exactly what you tell it to do. The only problem with a machine which does exactly what you tell it to do is sometimes you tell it to do really stupid things and it faithfully does it. And that can be really frustrating, hence why this video exists. And I just put this in here for laughs. So on this one here, I'd accidentally set the stock of my material to be a millimetre above where it was, so the milling machine thought it was a millimetre higher than it actually was. And at this point it's really great that the milling machine camera doesn't have any audio feed. It was really, really frustrating. So this is what I end up with in the end. So this is a piece of brass shim that's 50 micrometers thick, and that's what I get off the machine in the end. I know it's quite hard to see. And over here you can see a microscope image of not exactly the same design, the pads are bigger in this design. You end up with some burring at the edges, which are faithfully represented when you shadow mask it. So you do a weak nitric acid etch and it sort of smooths all the features over without actually affecting the width of the channel as much as a stronger etch would anyway. So this is some instrumentation, which up here we've got the probe station, which is a temperature controlled electronics probe station, which can range from about negative 65 degrees Celsius all the way up to 200 degrees Celsius. So I can probe in there and then take the temperature up and down and measure the thermal conductivity, changing the temperature. I've got some differential amplifiers in there, a 10K trimmer pot with a really low TCR, so it doesn't interfere with any of the other 3 Omega signals that I'm getting out. And something of interest, I didn't end up using it unfortunately, but I built a Howland current pump inside there as well, which is a positive feedback current pump type system which supposedly can provide a constant AC current source. I built it and I tested its bandwidth and everything. It seemed like it was going to do a great job, but then when I actually used it in the system, I'm not sure if it was something to do with my thermometer or maybe it's just not liking being attached to other components, but its bandwidth went crappy and it started producing really irregular waves and everything, so I pretty much ditched it and went back to using the voltage source, which is not ideal, but regardless, it's in there. And this little blue box down here is what I was playing around with at the start. So this is what's called a lock-in amplifier. So this is a tool that physicists are mostly familiar with, but does anyone here use a lock-in amplifier before? Know what it is? You have? Okay. So these are really cool. They work almost exactly the same as an AM radio demodulator. And the idea with them is that you get some incoming signal and you multiply it by the frequency that you're interested in. And then you get that frequency down at baseband with all the rest of it removed, and then everything else shifted up by 2 Omega. So you can then filter that off, and means you can get some really fantastic measurements of otherwise unmeasurable signals. So you can have 1 volt peak to peak or 2 volt peak to peak signal and 30 microvolt 3 Omega signal that you're interested in, and you can get it bang on every time. This one here is a Zurich Instruments one, which is pretty new and is what I was looking at earlier. So this is the interface, and this instrument's actually running downstairs. I was planning on doing a thing where I can tune into a radio station, because one side effect of them working really similarly to an AM radio is that you can actually tune into AM radio stations if you set all the filter constants appropriately. That didn't really work though. But this is what the interface looks like. You can set all your sweep parameters and do whole frequency range sweeps and everything. It's pretty cool.
Is this on digitally, with modulation or analog?
It's digital. It's an FPGA inside, I think. So these are the results that I got off the nanoparticle pucks, and I don't think Bob has actually seen this graph yet. But this was a sweep that I did from negative 35, I believe, up to 100 degrees. Above 100 degrees, one of the adhesives I'm using starts to burn, so I stopped taking it above there. Some interesting points to note. The thermal conductivity is nowhere where literature said it would be. This is at ambient pressure, and we were getting numbers around 100 milliwatts per meter Kelvin, and sort of a very heavy rise over the range of temperatures I measured, which is what you would expect. And there was a similar story with all the other compositions I tried. So this one here is for a 1, 2, 3, so one silica, 2 alumina, 3 carbon weight ratio puck. According to literature, they found this was like 8 milliwatts per meter Kelvin at room temperature, ambient pressure. The way that they measured it in literature, though, was they used a laser flash calorimeter, I believe. So they got a puck material, had an infrared laser pulse on the other side, and then waited for the pulse to emerge, and then measured the intensity and the time delay, and then they contained and changed that into thermal diffusivity and thermal conductivity. I wonder whether there was that test methodology is unsuitable for the material, given that carbon is sort of a radiation suppressor. I mean, it is, I'm not going to go all the way back, but it is absolutely lamp black when you look at it. And I wonder if there is some reason that they weren't getting any signal out the other side of that laser flash calorimeter. Because they made a larger tile and measured that with a guarded heat calorimeter, the same that Callahan Innovation measured it with, and they got a value which was closer to, well, almost exactly what I'm measuring here. So I wonder whether their numbers are correct on that or not. Looking around a little more, I found some literature on pure nanoparticle pucks or uncomposite versions of it. They found some interesting results, namely when they were under vacuum conditions, they had sort of similar results or on the same order of magnitude as other literature, in sort of 18 or tens of milliwatts per meter Kelvin thermal conductivity. Whereas at ambient pressure, they had 0.1 or 100 milliwatts per meter Kelvin, which is very similar to what I have. So one of the next tests I really want to do is to put these pucks into a vacuum chamber and see how much it changes, or see if I get numbers that are similar to that at all. Alright, so changing gear a bit, I'm going to move away from thermal conductivity and talk about a bit of a side project which we've been working on. So to start, consider this idea. You've got a microfluidic channel, and you have a laminar flow profile which is well established in there, and you are interested in the velocity at one point, one height x inside the channel. How would you go about measuring what the velocity in that plane is?
How fast is things moving?
Yeah, exactly. So that's one way. Particle tracing. So you put a bunch of particles or measure a height in the channel by focusing on it with a microscope, and then track how fast one particle is moving. That's one way. I believe there's confocal microscopy as well, but I don't quite understand how that works. Yeah.
Well, what sort of speeds are you interested in? What's the rate?
Very low speeds, like so in volumes it's sort of like microliters per hour, and then channel sizes are 100 micron square kind of thing. So it would be in the millimeters per minute kind of range, I imagine. So the idea here is if we have a thermometer on the base of this channel, and we know that we can provide a heat input into the system, and we can measure a temperature response from that system, surely that is going to depend on the velocity of the fluid above it. So say if we had a really low frequency driving this thermometer, the AC thermal waves might penetrate most or all of the way through the channel. But if you start to increase the frequency, then you're getting a temperature response only from, say, the bottom half, right? So the foundation idea is not so uncommon in solid systems. So this is what's called scanning thermal microscopy. The idea of this is you have a AC, like a 3 omega thermometer, like I've just been talking about, except embedded into the tip of AFM. So this can scan or raster across the surface and measure thermal transport away from the tip, and you can build up sort of a thermal conductivity profile or a heat transport profile over a whole range of places. So this is a topography of some, I think it's silicon nitride pillars on some silicon, and then they can take a corresponding thermal image of it and measure that thermal conductivity of the silicon beneath the pillars was much higher than that of the silicon nitride on the surface. So the idea with this system and the fluid sensor is really sort of the same idea, is that you can take a cross-sectional image of the fluid profile in a channel. So I have done some foundational work, we haven't quite got there with it, but this is what the chip I ended up fabricating looked like. So we have a microscope slide with the resistance thermometers like you were seeing on the slides before, a PDMS channel and then electrical leads coming out. This is the design that I made in the end. The serpentine nature of it was just to increase the resistance and get a higher signal to noise ratio in the experiment. And I presented this at a conference in February or March, January actually, and it seemed to work okay. I mean, I could correlate the thermal conductance linearly with flow rate, so I guess it works as a pure volumetric flow sensor, although that isn't typically useful or uncommon. However, what's interesting is the graph here of the 3 omega voltage versus, that's not meant to say flow rate, my apologies, that's meant to say electrical frequency, versus electrical frequency. And so you can see that at low flow rates there is sort of like a bigger marked difference between them. And however, as they sort of, this top line here is the zero flow condition, so that's when the fluid's stationary and presumably represents the thermal transfer function of water when it's stationary. And then as you increase the flow rate, it starts with a big difference and gradually converges at some point. So the idea is does the difference between these two, or any two of these lines, or the line in the no flow condition, does that represent the flow profile of the channel, and therefore can that be used to measure the velocity at one point or one depth inside the channel? So this was the preliminary work, and we're moving on with it now, and we thought that the easiest way to verify if it's actually putting or measuring the flow profile in general is to put a different flow profile through it and see if it substantially changes everything. So the only other flow profile we can think of, I guess, is one called electroosmotic flow, and that's instead of a parabolic laminar flow profile, you have the same velocity at every height in the channel. And although that seems like it might be physically impossible, it actually is possible using an electroosmotic flow driver, which involves 1 kilovolt voltage between the inlet and outlet of the channel, which scares me a little bit because there is also an electrical connection through to a $5,000 lock-in amplifier, and I don't know exactly how to protect it. It's a project for the future though. We also have a mechanical engineering intern who's working on simulating the project. I was really hoping to actually have some of his results to show you today, but I wasn't quite able to pull them together. He has actually simulated the electroosmotic plug flow profile, and what we've been seeing so far at least is we get the same profile in the no flow condition, except other lines don't converge to it. There is sort of a steady state offset through every single frequency range. So that sort of looks like it might be an indication that it's doing what we think it is, but there's no way to say for sure until we actually do some more work on it. Anyway, that's all from me. Thank you for listening. I'd like to thank my funders and also all of you for being here.
Yes.
relationship between the third harmonic and the temperature? What do you know why? What
Yeah,
the reason is?
I do know why. I just didn't want to put a slide full of maths there, but it's essentially when you're working with a current at some frequency, and then when you convert that to power, to heat energy, you square the current, so you end up with a second harmonic, which is the heat energy, right? Just the sine squared relation there, and that means you get the resistance oscillating linearly with the temperature, which is, so you get a 2 omega resistance oscillation, and then when you multiply that by the current again, you get a third harmonic in voltage.
What's your theory why the vacuum produces a lower thermal resistance? I don't think you mentioned it, but I know we've discussed it.
Yeah. So there's two competing theories here. One of which is that the whole premise of the packed nanoparticle beds depends on this radius of constriction being small relative to the radius of the nanoparticles. However, if there is any moisture which is absorbing onto the surface of them, you're essentially going to get a moisture wick which runs through there and increases that relative radius of constriction substantially. I tried running, so far I haven't been able to measure a difference. I've increased the temperature that I've measured into well above the boiling point of water, and then I've kept that running for I think 6 hours trying to measure a change relative to it, and it's just done nothing. So that's the moisture theory. The other theory is this is technically a porous structure. It is a porous structure, nowhere near that of aerogel or anything like that, but there's still gas contributing to the thermal conduction inside of this porous network. According to the same theorist who wrote this, there should be about like a 10% contribution of gases, but that's still nowhere near, so at this stage I'm not sure.
Do you see any other harmonics above the third harmonic at all?
There is a second. You can get the same information for the first and second. I haven't actually looked higher though. Yeah, sorry, I haven't.
No, I'm just curious if you...
No, I've never seen anyone look higher, honestly. People have done the same measurements by literally just the first and second harmonic, but I've never seen anyone use anything higher, no.
Has there been any applications with satellites, isolation in space, if this works in a vacuum?
Well, yeah, that's one of the big applications of aerogel, and this, this is like a, I guess you could call this a competitor for aerogel in that case. I think one of the things that aerogel has over a packed structure is that it's also very mechanically sound and it's quite light for volume. So while this might be able to beat an aerogel and say pure thermal insulation performance, it's also 100 times as dense as an aerogel. So while you might be getting, say, 6 milliwatts per meter Kelvin from this and 20 milliwatts per meter Kelvin from an aerogel, you're still getting 10 times the weight for the same thickness of material. So yeah, so that's the way it goes. But yeah, they do actually use these types of aerogel type materials in most satellites to keep them warm.
Yeah.
So what sort of issues do you have with your electrolyte boundary with your measuring of your fluids going through? So what are you using? So gold electrodes, eh?
Yeah, gold electrodes. At the moment, we've just been using deionized water and hoping that it doesn't conduct, really. The problem is, the reason we haven't insulated it is essentially it's just difficult to bond a PDMS chip to something else other than pure glass, soda-lime glass. So the plan for the electroosmotic driver is to put some other layer on top of it as well, and then just try lots of mounting pressure, just get a large clamp to push it down to stop it from leaking.
So what sort of source impedance have you got there?
Source impedance from my driver.
Between the electrodes, so you measure it. What sort of source impedance is it? Yeah.
So you mean just the resistor? What's the resistance?
There's deionized water and a couple of electrodes in it. So what is that impedance?
It is like 8. It depends heavily on the design that I'm using, but I think the serpentine one that I was using was 8 ohms, or thereabouts, between 7 and 8 ohms. And I don't know what the resistivity. Oh no, I do know what the resistivity of deionized water is. It's 18.6 mega ohms per centimeter. So the difference is pretty substantial.
So you've got pretty high impedance between the electrodes.
Yeah.
They're not discontinuous electrodes. They're not electrodes in the chemical sense. It's just a heater line. So you're not measuring via the liquid. The liquid is in contact with them.
Right.
Yeah.
You don't, there's no discontinuity where you would have to have a current flow through the liquid.
But a conductive liquid would affect your results.
Yeah, it would. Yeah.
And you need to know the thermal conductivity of the liquid to a degree.
Yeah. Well, technically speaking, if I took the slope of this no flow condition, I can actually just measure the thermal conductivity as long as I know as long as I know that the fluid is perfectly stationary. I can take this as the control case, and then it's just the difference between the control case and that, given all things staying the same after that.